Many people calculate very carefully before buying an EV, thinking about not having to change engine oil or transmission fluid, and barely even wearing out the brake pads. It is definitely a money-saving financial tool. But when you have driven 20,000 to 30,000 kilometers and go to the tire shop for your first tire change, seeing a quote of 30,000 to 40,000 NTDs for specialized tires will absolutely make you gasp. At this moment, a huge question will surely pop into your mind. Isn't a tire just a black, circular piece of rubber wrapped around some air? As long as my rim size, width, and aspect ratio are the same, why can't I just go to a hypermarket and pick the cheapest gas car tire and force it on? What exactly makes EV-specific tires so expensive? Is this the car manufacturers and tire makers teaming up to rip off us EV owners? If you've ever had this thought, or are even currently planning to change to a cheap set of gases, car tires to save money, please drop that idea immediately. In today's video, we are going to use the most hardcore underlying engineering perspective to thoroughly dismantle the physical limits behind EV tires. After watching, you will understand that putting regular tires on an EV isn't just destroying the car's handling, it is also playing a joke with your own life safety. Physically, as long as the size is right, tire shops can definitely help you fit a gas car tire onto an EV. But for every kilometer you drive on the road after that, you are bearing a huge risk of losing control. Because the reason EV tires are so expensive is that tire engineers must solve for extreme physical challenges on them that are almost impossible to occur simultaneously on traditional gas cars. Let's first look at the first and most fatal challenge, which is also the original sin of all EVs: payload hell. Everyone knows EV chassis are paved with lithium batteries, but many people have no concrete concept of this weight. Let's look at it from the physics of energy density. 1 kilogram of gasoline contains about 13 kilowatt-hours of energy, but 1 kilogram of top-tier lithium batteries can store at most 0.25 kilowatt-hours of energy. This means that to achieve the same driving range as a gas car, EVs must carry an extremely massive dead weight of batteries. This causes an EV in the same size segment to typically be 20% to 30% heavier than a gas car. A Tesla Model Y, which is about the same size as a Honda CR-V, easily weighs close to 2 tons empty. If it is a Porsche Taycan or a large pure electric SUV, exceeding 2.5 tons is commonplace. What is the concept of this extra 400 or 500 kilograms? It is equivalent to your car always being fully loaded with 5 muscular adult men. This massive dead weight is a physical disaster for ordinary tires. The actual contact patch area of the 4 tires on the ground is actually only the size of 4 postcards. If you install a regular gas car tire, you might not see anything abnormal when stationary. But when the car starts moving, dynamic physics begins to take effect. When you make an emergency lane change on the highway at a speed of 110 kilometers per hour, or when cornering on a winding mountain road, this 2-ton behemoth will generate extremely terrifying lateral stress. The sidewall structure of an ordinary gas car tire simply cannot withstand this level of side thrust. The sidewall, which should support upright, will twist severely, or even fold and collapse. This will make your car feel like driving a boat on the sea, with an extremely vague road feel. Under extreme conditions, such as a moose test for an emergency obstacle evasion, excessively deformed sidewalls will cause instant unseating from the rim, or internal ply cords breaking directly, triggering a blowout. Therefore, EV-specific tires must comprehensively strengthen the sidewall structure from the inside out. If you squat down and look at the code on the sidewall, you will see the XL Extra Load mark. In recent years, for increasingly heavy high-end EVs, The industry has even introduced a brand new HL high load standard, which can bear 10% more weight than XL. To achieve this standard, the interior of the tire must incorporate higher, tensile steel wire layers and thickened double-layer plies. This directly raises the first wave of material and manufacturing costs. Having solved the massive weight, we face the second challenge. This challenge is closely related to our previous video, the motor's torque tearing and relentless fatigue load. We emphasized in the last episode that the physical nature of a motor is to erupt with 100% maximum torque the moment it is electrified. When a traditional gas car starts, the torque slowly climbs with the engine speed, providing a gradual buffer for the power. But the moment you step on the accelerator of an EV at a green light, violent torque easily reaching 500 or 600 Newton meters, without any transmission leg, is directly slammed into the wheels like a sledgehammer. Imagine this instantaneous burst of violence, pressing ruthlessly against those postcard-sized pieces of rubber, tearing desperately backwards on the rough asphalt road. Ordinary gas car tires, with their soft compounds and fine tread patterns designed for comfort, simply cannot withstand this kind of devastation. Under strong torque, an invisible microslip phenomenon occurs on the tire's surface. Microslip. With every start, the rubber is ruthlessly milled and stripped away. But that is not the most tragic part. The unique kinetic energy recovery system of EVs, namely the one-pedal driving mode, makes the situation for tires even worse. When you release the accelerator while driving at high speed, the motor instantly turns into a generator, producing a strong reverse drag torque. What does this mean? This means that your tired, which just a second ago was being desperately torn forward by strong positive torque, is being crazily dragged backwards by reversing torque the next second. In materials engineering, this is called high-frequency fatigue loading. What is even worse is the dynamic shift of the center of gravity. When kinetic energy recovery activates, the front of the car will experience a severe nosedive effect. The 2-ton weight of the car instantly presses forward onto the 2 front wheels. The front wheels not only have to withstand the reverse torque, but also bear the sharply increased weight. This causes the wear rate of the front wheels to be far greater than that of the rear wheels. Under this kind of back-and-forth pulling, ordinary rubber molecules will quickly age and break, even resulting in chunking, where pieces of the tread peel off. This is why your driving habits haven't changed, yet your tires are done before reaching 20,000 kilometers. To solve the tearing, engineers must enlarge the central rib pattern and use an ultra-wear-resistant compound. At the same time, we must give all EV owners a strong engineering warning: you must rotate your tires more frequently than driving a gas car. It is strongly recommended every 7 to 8,000 kilometers to strictly perform a front-to-back cross tire rotation to evenly distribute the devastation of this forward and reversed stress. This is the only physical way to extend the life of this set of expensive tires. Next is the third challenge. This is the dead end that gives global tire engineers the biggest headache: the range of anxiety of EV owners and the extreme tug-of-war of the tire's magic triangle. The tire industry has an unbreakable magic triangle of physical laws, grip, wear resistance, and low rolling resistance. These 3 conflict with each other. Improving one or two of them will inevitably sacrifice the third. Gas-powered performance cars will use soft rubber for grips. The price is high rolling resistance, making them more fuel-consuming. But the owner can just make an extra trip to the gas station. However, EV owners have an anxiety about battery levels engraved in their genes. If the resistance is too high, precious driving range could instantly evaporate by 30 to 50 kilometers. But you absolutely cannot, for the sake of saving power, make the tire as hard and slippery as a rock. Don't forget you are carrying a 2-ton vehicle weight underneath, sacrificing grip. When encountering an emergency, braking, the powerful inertia will make the car completely unable to stop. It needs to run far to save power, needs to be able to stop at any time, and also needs to be super wear resistant to handle torque. To solve this contradiction that violates common physical sense, tire companies can only invest astronomical amounts in materials chemistry R&D. They added a large amount of silica into the rubber compound. This magic silica compound is extremely clever. It can stay soft during high-frequency deformation, such as emergency braking, biting tightly onto the road surface. Yet during low-frequency deformation, like highway cruising at a constant speed, it demonstrates extremely low energy loss. But the price of this magic compound is extremely high. Silica and traditional rubber are as mutually insoluble as water and oil. An expensive silane coupling agent must be added, and it must be done in extremely precise high-temperature and high-pressure mixing equipment, going through an ultra-long mixing time before it can become uniform. This not only significantly increases raw material costs, but also makes the power consumption and wear rate of the manufacturing machines skyrocket. This massive cost, without a doubt, piles up onto the consumer's price quote. Finally, we arrived at the fourth challenge. This is a test of the limits of human ears. The maddening noise brought about by extreme quietness. The engine noise and exhaust sound of a traditional gas car are actually excellent environmental white noise, cleverly masking the tire noise transmitted from the chassis. But after switching to an EV, the noisy internal combustion engine is completely removed. The cabin is as quiet as a library late at night. Losing the cover of the engine sound, the physical phenomena become incredibly cruel. When the tire rolls and compresses at high speeds on the road, the air inside the tire generates strong resonance. This is acoustically referred to as cavity resonance. The principle is just like blowing air over the mouth of an empty glass bottle inside an extremely quiet EV. This low-frequency booming sound is magnified infinitely. Not only is it harsh, but long-distance driving will also cause severe tinnitus and motion sickness. The most effective, but also most brute force physical noise reduction method is very labor-intensive. If you cut open a Michelin acoustic or Continental Contisolent, these high-end EV-specific tires, you will find that the inner wall of the tire has actually been manually glued with a full ring of thick polyurethane acoustic foam. This ring of foam is like sound-absorbing cotton on the walls of a recording studio, capable of perfectly absorbing and scattering air resonance waves. Think about it on a highly automated tire assembly line. How troublesome it is to add this process of applying special adhesives and precisely attaching the foam. This ring of foam must also be glued extremely symmetrically and balanced. Otherwise, when the tire spins at a high speed of 120 kilometers per hour, it will cause severe center of gravity shift and vibration. This tedious manual and high-precision machining process naturally makes the price of this tire skyrocket. Hearing this, quick-witted viewers will definitely think in reverse. Since F-specific tires are so amazing, able to bear heavy loads, are super wear-resistant, have ultra-low resistance, and even come with built-in silent foam, if I'm not short on money, I'll just buy the top-tier EV tires and install them on my regular gas car. Wouldn't I be able to enjoy ultimate quietness and a super long lifespan? This is fundamentally a dimensional strike. This logic sounds perfect, but absolutely do not do this. In chassis engineering, this is called dropping a rock on your own foot. There is a famous saying in automotive suspension engineering: 1 kilogram lighter below the springs is equal to 10 kilograms lighter above the springs. Unsprung mass, the weight below the shock absorbers, has a devastating impact on vehicle dynamics. EV tires are packed with high-strength steel plies, thickened sidewalls, and had a whole ring of foam glued in. So the weight of a single tire is vastly heavier than an ordinary gas car tire. Gas cars are already lit, and their shock absorber springs and dampings are set for lightweight tires, suddenly switching to for incredibly heavy EV tires when driving over potholes. The shock absorbers simply cannot hold back the massive inertia, bouncing crazily up and down. The comfort of the cabin would be directly ruined, the road feeling becoming rigidly stiff. What's worse, the heavy tires will significantly increase the moment of inertia. The engine must expend multiple times the effort just to get these four big iron balls turning. The result is that starting off feels extremely sluggish, and fuel consumption not only doesn't improve, but rather shoots up linearly. As for the silent foam you spent big money on, sorry, the engine noise of the gas car has long overpowered it. You simply cannot hear the difference. This is like telling a sprinter to wear a weightlifter's lead shoes to a race, putting the cart before the horse. Speaking of which, finally, I need to help everyone avoid landmines by exposing the most confusing traps currently on the market: EV-ready universal tires. As the market share of EVs skyrockets, major tire companies, in order to save on molding and inventory costs, began launching universal tires marketed for both gas and electric vehicles. They slap on an EV-ready label, highlighting an approachable price. But in the hardcore engineering world, universal often means compromising on both sides to ensure it doesn't feel too bumpy or rigidly stiff when installed on a lighter gas car. Universal tires dare not make their sidewalls up to the top tier HL specification of purebred EV tires. When you are driving a 2-ton EV aggressively through a corner, its supporting forces will definitely be discounted to cater to the market price. The inside of universal tires typically also doesn't come standard with that ring of expensive acoustic foam. Getting on the highway, the low frequency, the booming sound will absolutely make you regret saving those few $1,000. So, for tires labeled as EV-ready, our engineering advice is to learn to read the sidewall codes yourself. Squat down and see if there are XL or HL markings. Look at its treadwear index to see if it has been excessively compromised. Most critically, press down on the sidewall with your own hands and verify whether there is actually a physical acoustic foam inside. If there is no substantial physical countermeasure, then at best, it is just a slightly fatter gas car tire. In conclusion, an EV tire is a product combining high load capacity, tear resistance, low rolling resistance, and extreme quietness from cutting-edge materials engineering. This is an absolutely uncrossable chasm in the underlying physics between gas cars and electric vehicles. Putting gas car tires on an EV to save money causes skyrocketing risks of losing control, terrible range, and premature retirement under 20,000 kilometers. Putting EV tires on a gas car will only result in sluggishness, high fuel consumption, and disastrous bumpiness. Many people buy EVs calculating every cent of gas money saved, only to vomit it all back out with interest when it comes time to change tires. After driving an EV for 10 years, factoring in this expensive tire wear, insurance premiums, and depreciation, is the total cost of ownership TCO really lower than a gas car? This topic is truly both brutal and fascinating. In our next video, we'll pull up an Excel spreadsheet and calculate its item by item for you to see. Dedicated parts for dedicated cars is not just a marketing slogan. It is the most basic respect for the limits of physics. If this video resolved your maintenance myths, please help me hit the like button, subscribe, and share it with friends who are hesitating about buying a car.